All right, we are now ready to start a new section of the class. We've more or less finished with the foundations for thermodynamics, and we're ready to move on to the main area of application. And that means looking at what thermodynamics has to say about chemical equilibrium. We've talked about it in a general way. Now we need to do something a good deal more specific. We've talked about the first law, we've talked about the second law, we've talked about equilibrium states, we've talked about energy and entropy. We're going to apply all those ideas now to chemical equilibrium. So to do that, the very first thing we're going to do is consider the simplest possible chemical reaction there is, and that's just a single reactant going to a single product and coming to equilibrium eventually. We're going to do the same kind of thing when we start talking about chemical kinetics towards the end of the class. But for the moment, we're just going to consider the equilibrium properties of this chemical reaction. So we're not going to consider anything about how fast it goes, only about at what the concentrations or other related activities, if you like, for the reactant A and what the concentration for the product B are when they reach equilibrium. This very simple chemical reaction, despite the fact that it's so simple, applies to a whole bunch of different cases. Let me give a few examples. First of all, to any kind of sort of internal shape change or other kind of thing that happens with simple molecules, like, for example, this cis-trans isomerization. That's one obvious case that this formal chemical reaction applies to. Also to conformational changes of proteins or other molecules, so an open protein that's in some kind of open state goes to some kind of closed state, for example, upon binding a substrate molecule, say. Or a transition like this one where you have a DNA molecule that melts and comes apart to its single strands. Or a protein molecule, let's say it's something that looks like this, that melts or denatures and comes apart into a random coil configuration. Those are usually treated as two-state systems, even though in principle there's a whole bunch of other states in there. And in that case, this would be A and this would be B and so forth. This would be A, this would be B. But it also, so those are all chemical reactions. Those are chemical reactions proper, but the whole idea, this general form, applies also to things that we don't normally think of as chemical reactions. So transfer processes, for example. If I have some sodium on, if this is a membrane, for example, and this is some kind of channel, and a sodium ion traverses from the inside to the outside, the sodium atom hasn't changed its chemical properties at all, and yet we can think of it as a chemical reaction. The sodium atom, while it's on the inside, would be counted as A, and when it's on the outside, it's counted as B, even though there's obviously no change in the chemical nature of the sodium atom in doing that. Thermodynamically, the fact that there's no change in the chemistry doesn't matter. All the concepts and mathematics and relationships that apply for these proper chemical reactions up here will also apply for this, what you might call an improper chemical reaction, I guess, down here. Likewise, here's another type of transfer process. You have some molecule dissolved in water. There's a layer of oil or oily or hydrophobic solvent up on top of that, let's say hexane or something like that. And for one reason or another, to some extent or another, that dissolved molecule transfers itself from one phase to another. That's called partitioning, right? And there's a zillion partitioning reactions that occur. For example, in this membrane up here, if you've got some small molecule in solution here, it can partition into the membrane because the membrane's very hydrophobic compared to the surrounding solution. And there's a million other kinds of situations where partitioning happens. For example, if I've got a water phase here And there's a gas phase up above. That's another type of partitioning, right? So some molecule in the water phase evaporates out into the gas phase. That's another kind of partitioning. Anytime some chemical species transfers itself from one phase to another, that's a partitioning process. And that can also be considered to be a chemical reaction where the same type of molecule, X, whatever that is, transfers itself physically from one place to another. Then that also can be treated by this very simple chemical reaction. Also phase changes. So I've got liquid water over here, I've got water vapor over here. That can be written in the following way as a chemical reaction. And so the liquid water would play the role of A, and the gaseous water would play the role of B. And so that also falls under this type of chemical reaction. And here's, of course, another chemical or another phase transition going from ice to water. So the solid, the ice, is the A, and the liquid in this case would be the B, and so on. So this very simple chemical reaction actually covers a very wide variety of cases. In fact, maybe a bigger variety of cases than almost any other situation. We're going to deal in the end, let's see if I say that down here, with more complicated cases, with more general chemical reactions eventually, but it's useful to deal with the simplest cases first. That's true at every level of science. Even Albert Einstein and Enrico Fermi and all the giants of physics always deal with the simplest cases first, because they're usually very instructive and very illuminating. They may not tell you everything you want to know about all the complex cases, but they tell you the principles and the ideas that are important for those complex cases. And so always deal with the simplest case first. All right, so we're going to consider the following situation. We're going to have a temperature bath and a pressure bath. So this chemical reaction up here is taking place at constant temperature and constant pressure in the presence of surroundings that act as baths for temperature and pressure. And then the chemical reaction is taking place, and under those conditions, we have seen earlier in our foundation sections that the change in the entropy of the universe, or minus T times the change in the entropy of the universe, is the same thing as the change in the Gibbs free energy. And since this temperature is a constant because we've got a bath here, the minus T doesn't really change anything. The change in the entropy of the universe is still proportional to the free energy change. And therefore, we're going to be interested in looking at the free energy change. The variables that matter for this experiment, or for this situation, are therefore the temperature and the pressure, of course, from the baths, and then the mole numbers for our two chemical species, A and B. And those are the only variables that we care about for this particular case. If we then write out the form of the first law that applies for changes in Gibbs free energy, or the differential expression for Gibbs free energy. Remember, there was that section of formal properties, and I told you that we were going to use them. And here's the first case where we're using them. We're writing out the differential expression for the Gibbs free energy. Then that differential expression is equal to minus S times dt plus volume times dP, plus terms that involve all the chemical species, the chemical potential for each species, and the change in mole numbers for each species. And so since there's only two species, that's chemical potential for A, mole numbers for A, and the same thing for B. We have a couple of constraints, actually three constraints. First of all, the temperature has to stay constant, right? If we've got temperature, if we're talking only about equilibrium states, and we have a T bath present, then that means this dt has to be 0, and likewise the pressure has to stay constant, so the dP is equal to 0. So these first two terms just disappear. That's one of the big reasons for using Gibbs free energy like this. It gives us a function that's already written in terms of the variables that are most useful to consider, namely temperature and pressure. We could do all this with the entropy of the universe itself, but then we'd have things like du and dV to worry about, and those are unnatural variables for these sorts of conditions. And so using Gibbs free energy has the advantage of right away putting us into the sort of the right ballpark for what we want to do. All right. There is another constraint. So those are two of the three constraints. There is another constraint, and that constraint is that whenever a molecule of A is destroyed, a molecule of B has to be created, and vice versa. And that means that the changes in the mole numbers for A and B are not independent of each other. They're related to each other. Whenever B gets created, A has to be destroyed, and vice versa. So dNB is equal to minus dNA. We plug that relationship up in here and here. Basically, we can eliminate this variable. That becomes minus dNB, and then we can factor it out, factor the dNBs out here. And now we get the following, that now, after boiling things down a little bit, the change in the Gibbs free energy is equal to the difference in the chemical potentials on the two sides of the chemical reaction times this small change in the number of moles for the product, species B. And if we divide both sides by this product concentration or product mole number change, then we get that the rate of change of the Gibbs free energy with respect to the mole number changes in B is equal to the difference in the chemical potentials. Well, what is this quantity over here, this derivative of G with respect to mole numbers? It's a driving force, right? It's the driving force for the chemical reaction. We can write it here as delta mu, a change in the chemical potentials from going from one side of the reaction to the other. As we go from the reactant side to the product side, there's a change in the chemical potentials. And so this is products, right? This is the chemical potential for the products. This is the chemical potential for the reactants. And there's a change in chemical potential as you go from one side to the other. A has a different chemical potential than B does. And that difference is the driving force. That's what this is saying, right? The dG is proportional to the entropy change for the universe, and therefore is proportional to the driving force for chemical change. And therefore, this difference in chemical potential is also the driving force for chemical change. So I put here that dG dN is the change in Gibbs free energy, and therefore proportional to the change in the entropy of the universe per unit of creation of B. And so a good quantity to give the driving force for a chemical reaction. Let's look at what that means. That means that if the chemical potential between the two sides is greater than 0, which means that the chemical potential for the products, for B, is greater than the chemical potential for the reactants, A, so the chemical potential goes up as we go from the reactants to the products, then that means that the Gibbs free energy is rising when we create B molecules. And that means that the reaction, that the entropy change of the universe will be going down, right, because of the minus sign here, right? There's this minus sign, so when dG goes up, ds is going down. That means that's an unfavorable change. That means that the reaction won't go forward, it'll want to go backwards. And so a chemical potential difference that's greater than 0 for a chemical reaction is a condition for the reaction to go spontaneously backwards. If the chemical potentials are balanced, then we have force balance, right? Chemical potential is a force for mole number change, and the difference in chemical potentials is the net force. If that difference is 0, then there is no net force, and that means we have force balance and we're at equilibrium. On the other hand, if the difference in chemical potentials is less than 0, then the Gibbs free energy decreases when we transfer some A to B, when we move the reaction forward, and that's favorable. That means the entropy of the universe increased, and that means the reaction will spontaneously go forward. All right, so just to repeat, The change in the chemical potentials between the two sides of the chemical reaction is the driving force for the chemical reaction. It really boils down to a fairly simple thing. If you want to know whether a chemical reaction or anything that can be thought of as a chemical reaction, like a phase change or a transfer process, if you want to know if that's going to go spontaneously forward, look at the chemical potentials on the two sides of the reaction. If the chemical potential on the product side is high, that's unfavorable, right? That's a high chemical potential. Things want to move towards low chemical potential, so that means the reaction would go the other way, would go backwards. On the other hand, if the chemical potential on the product side is lower than the chemical potential on the reactant side, then the reaction will go forward. It's favorable to go forward. All right. As I said, so far we're considering only the simplest cases. A goes to B. But of course, we're eventually going to want to consider much more complicated chemical reactions of any complexity, in fact. And so here's sort of the generic form for a complex chemical reaction. And we will derive eventually that in that case, everything I've set up above stays the same, doesn't change, except that we change the definition for this difference in chemical potential. Instead of just having one product now and only one reactant, we have, well, two products and two reactants, and we could have 3 or 4 products and 3 or 4 reactants if we wanted to, right? And then what you want is the chemical potential, the effective chemical potential for the products as a whole, not for any one species, but for all the products, and likewise a chemical potential for the reactants. And it's the difference between those two that should be the driving force in that case. And we will see that this effective chemical potential for the products is just the chemical potentials of the individual species weighted by their stoichiometric coefficients. This is products minus reactants weighted by stoichiometric coefficients, as we've seen in a whole bunch of other cases like this. This sort of rule, products minus reactants weighted by stoichiometric coefficients, applies all over the place. In many situations it applies here. All right. So even when we go to the more complicated case, most of what I'm saying right now, basically all of what I'm saying right now, is still going to apply. And that's the value of looking at simple cases like this. Right? I said at the beginning that we're going to look at this simple case. Now you see why. Because when you go to the complicated cases, the basic ideas don't change. Everything more or less stays the same, just a little bit more complexity has to be added. In this case, we have to look at a little bit more complex definition of what we mean by the chemical potential of the products and the chemical potential of the reactants. All right, so here's some examples. Again, we have this isomerization process, cis-trans isomerization. Let's suppose the chemical potential for the B side here, for the cis species, is actually higher. You might imagine, I'm pretty sure that it is, in fact, the case that that's true, because these two N groups here kind of bump into each other or clash with each other a little bit, which raises the chemical potential on this side a little bit. And that means that the equilibrium will favor the trans form. It doesn't favor it very much, I don't think, but a little bit favors the trans form. If I have a situation like this, so this is a chemical reaction. Here's a molecular transfer process where you have some sodium on the inside, some going to sodium on the outside. Let's suppose that the concentration is high on the inside and the concentration is low on the outside. Then it turns out, we will see when we look at what the chemical potential is a little bit below, that high concentration of a species corresponds to high chemical potential for the species, and low concentration corresponds to low chemical potential for a species. So here's the formula. We've seen this before. This is our equation of state. We saw this earlier in Chapter 9. And you can see what it means, right? If this concentration goes up, well, the logarithm doesn't change the fact that this whole term, this whole N term goes up, and that means the chemical potential goes up. So when the concentration goes, so it's not, I mean, the chemical potential isn't the same thing as concentration, but it goes up when concentration goes up and it goes down when concentration goes down. So that means that this high concentration on the inside, that's the high chemical potential case, and this low concentration on the outside, that's the low chemical potential case. And so you'll get spontaneous transfer of sodium from the inside to the outside. And you can kind of see on an intuitive level why that should be so, right? If you try to pack sodium, if you imagine sodium ions trying to pack into this highly concentrated place, that seems intuitively to be lowering or reducing the number of microstates available to the sodium ions, right? You're trying to basically, if you think of them like gas molecules, and you've got a whole bunch over here and few over here, and you try to pack those few over into the high concentration side, then you're reducing the number of microstates available to the sodium ions. On the other hand, if you move them the other way, then you're increasing the number of microstates available to the sodium ions. And this expression for chemical potential, and chemical potential generally, is accounting for those kinds of changes. We'll see a great deal more that this analogy right here, where you think of the molecules as if they were just points moving around in space, applies almost exactly to every chemical reaction. This logic that we looked at in the very first day of class, and we will continue to see as we move on through the class, applies universally, really, to every chemical reaction. All right, here's another couple of cases. Let's suppose that I have some ice and some water. That's A and B in this case. And let's suppose we're at minus 5 degrees centigrade and 1 atmosphere. Under those conditions, the water wants to freeze, right? The stable state is the ice state and the water is the unstable state. That means that the water is the high chemical potential state, and the ice is the low chemical potential state, so the system will freeze. Moles will transfer from the water phase to the ice phase. On the other hand, if we change the temperature, go up by 10 degrees to plus 5 degrees centigrade, now the ice is the unstable state and the water is the stable state, and moles will transfer the other way. So which way we're going, which way is actually the high chemical potential state, which thing is the low chemical potential state, depends on temperature, among other variables, temperature and pressure and other things, properties of the molecules and so on. All right. So that's the basic rule. The difference in chemical potentials between the products and the reactants is the driving force. That driving force is related to the number of microstates available when you transfer from reactants to products. And we will see with many more examples as we go along how that works, and you can get an intuitive feeling for whether or not a chemical reaction will go from that. In order to help with that, we're going to now look at where this equation of state for chemical potential comes from. I wrote that down earlier, but didn't make much in the way of commentary on it because I was expecting to make those commentaries now. And so now we're here. We need to understand this equation of state. It's very important, and it's saying some very important things. This second term in the equation of state is accounting for translational degrees of freedom, or translational microstates, and nothing else. All the chemical information is actually buried in this constant. But in order to see that that's really the case, let's do a little bit of statistical mechanics. I'm going to introduce a simple model, and I'm going to use that model to actually derive this equation of state. This is the job of statistical mechanics. It's finding equations, thermodynamic equations of state from molecular properties is what statistical mechanics was invented to do, and it's what statistical mechanicians spend a lot of their time doing. And so let's see how that works in this case. This is probably the only example, I think, where we're going to actually do a little bit of practical statistical mechanics in this class. And I'm going to be a little bit vague and not very rigorous and jump over a lot of steps because otherwise we'd end up spending too much time on this. But I do want to show a little bit for two reasons. First, so you can see how statistical mechanics works, how you can use StatMech to get important thermodynamic relationships like this one up here. There's really no thermodynamic relationship for chemists that's more important than this one. Almost all of chemistry, as we know it, comes from this equation of state. And then also to show you what this equation of state actually means. The statistical mechanical model will show us where this second term comes from, where this first term comes from, and what kinds of interactions and properties and changes are being accounted for by those two terms. So let's consider a gas of water molecules, or any other molecule. It doesn't really matter what kind of molecules. I drew water molecules here because they're simple and common. In that case, it is possible to show that the canonical partition function, this is the same Q that we've been using all along when we talked about the Boltzmann distribution. So this is straight from statistical mechanics. That partition function has the following form. It has two factors, this dark green factor here, and then this blue factor. And the dark green factor accounts for only one thing. It accounts for the translational microstates of all the water molecules in our system. In other words, it only accounts for the fact that the water molecules can move around in the box. That's the only, if you replace these water molecules with helium atoms or with proteins or anything else, any other molecule at all, this term, this first term, would not change at all. It doesn't have anything, doesn't know anything about the molecular properties. It only knows that the molecules can move around, and that's all that it's accounting for. Everything else, all the molecular properties are buried in this second term, and there's actually a lot of complexity. This little thing that I've called Q molec here, that's a complicated thing inside. I'm burying a whole lot of complexity by, under that little name, under that little Q. It accounts, for example, for the fact that molecules can rotate and the fact that they have a moment of inertia. If this were a different class, we would talk in detail about how these things are accounted for inside this term, but we don't have time for that in this class. And also for the vibrations, for bonding and molecular shape, for every other property of the molecule. That's all buried inside this second term. All right. Let me point out one more thing, and that is that this term may look a little obscure and complicated, but we've seen another term like it earlier already when we were talking about what entropy is and what microstates are, what W is. We saw that W, the number of microstates available to a box full of structureless particles, is equal to the volume of the box to the power of the number of molecules in the box divided by n factorial. And you can see that that's very close to what we have up here. We have v to the n here and n factorial. There's this extra, that's a capital Greek lambda there. We have this extra thing down there, and that does have some effect. It's actually just a little bit of extra detail that's been added. But the essence of this term is the same as the essence of this term, and both things are in fact accounting for the number of microstates that's available to the system just because the molecules can move around inside the box. All right, now that we have the partition function, remember that the Helmholtz free energy is very closely related to the partition function. Remember, entropy is equal to Kb log W. W is the number of microstates for an isolated system. Q is the number of microstates for an open system that's in contact with a temperature bath. So these two relationships are very closely related to each other. They're very analogous to each other. There is a couple of differences. First, there's a temperature in here, and then there's a minus sign in here. So the Helmholtz free energy is a free energy. It's not an entropy. But it is proportional to the entropy of the universe for an open system. And so these two things are even more closely related to each other than would be apparent at first glance. And so this relationship between the Helmholtz free energy and the canonical partition function is doing very much the same kind of thing as this Boltzmann relationship between the entropy and the number of microstates available to the system. Yeah, and let me just reiterate that this partition function, this Q, remember, is a measure of how many of the effective number of microstates available to the system. We saw that with our very simple examples in the last few sections of the class. And now we're kind of seeing it here, right? At least this first factor is the same thing pretty much as this W, number of microstates available. And this is just accounting for all the microstates due to other properties of the molecules, right? Due to their rotations and vibrations and stuff. So you can see that it's plausible that this relationship is giving us the number of microstates, the effective number of microstates available to the system. All right. If this is true, then from one of our earlier relationships, again, one of our formal relationships that we wrote out earlier, the chemical potential is equal to the partial derivative of the Helmholtz free energy with respect to whatever mole number is relevant. If it's species A, then it will be D, then the chemical potential for A. Here, let me write that better. If I'm looking for the chemical potential of species A, that would be the partial derivative of the Helmholtz free energy with respect to the mole numbers for A. If we were doing the same thing for B, it would be the partial derivative with respect to the mole numbers for B, and so on. So I didn't specify which chemical species it is because it applies to any chemical species, any specific chemical species. All right, so that's the relationships we're going to use. Notice the chain of logic. We've got the partition function up here, which we can get from molecular properties. I didn't tell you where this came from, and it's a fairly long derivation. In fact, that's why I didn't put it in. But it can be derived from molecular properties. Once you've got that, you can plug that in to get the Helmholtz free energy. And once you've got the Helmholtz free energy, you can take a partial derivative, and that gives you the chemical potential. Here is the algebra for that. So here I've plugged our expression for Q, all this stuff. Let me clean that up a little bit. It's getting messier and messier as I put more arrows on it. Let me clean that stuff up a little. So I'm taking this, I'm plugging it into, let me clean up here too. I'm plugging it in right there. I'm doing a little bit of algebra, and that gives me this. So believe it or not, all of this came from plugging that expression for Q in there and then taking logs and doing a little bit of algebra. Now I take a partial derivative with respect to mole numbers, and this big N is the number of molecules. That's equal to the number of moles times Avogadro's number, and so the number of moles is equal to big N over Avogadro's number. I use that fact here, so now I'm taking the derivative of the Helmholtz free energy with respect to the number of molecules rather than the number of moles. And now it's just a mathematical process. I take the partial derivative with respect to N here of that, and I won't go through the algebra because it's fairly elaborate. But it boils down, after you take the derivative and do a little bit of rearranging, to a chemical potential is equal to a leading term that involves the properties of the molecules. It involves this Q, this little q, that depends on the properties of the molecules, plus a second term that doesn't depend on the nature of the molecule at all, but does depend on the number of molecules per unit volume. That's concentration, right? Molar concentration, for example, is number of moles per unit volume, but that's just equal to the number of molecules per unit volume times 1 over Avogadro's number. So it's proportional. Molar concentration is proportional to this number, this quantity that's appearing here. And so this quantity right here is also proportional to the activity for the molecules in question. And so we have right away from our derivation an important conclusion, and that important conclusion is that the chemical potential always breaks down into two terms, one of which can be thought of as a constant because it doesn't depend on concentration, but does depend on the properties of the molecules, and a second term that doesn't depend on the properties of the molecules, but does depend on concentration. We're going to see that that pattern, or that form, that mathematical form, holds all the way through. All right, after a few more steps of derivation that I won't fill in, we get our original equation of state. The chemical potential is equal to some constant, the standard state chemical potential, plus an extra term, which accounts for variations in concentration. If I change the concentration of a chemical species, I'm changing its chemical potential, and this term accounts for that. I'm changing the number of microstates available to it, right? And therefore changing its chemical potential, and this term accounts for that. All right. A couple more comments, and then I think we'll quit for this lecture. This is really just saying what I just said. This first term, the standard state chemical potential, accounts for all the molecular properties, accounts for mass, for the bonding that occurs inside the molecule, for the shape of the molecule, for the rotations and vibrations of the molecule. It also accounts for what solvent the molecule may be dissolved in, or if it's a gas, for the fact that it's a gas, for the fact that it's in vacuum in that case. It also depends in general on the temperature and pressure, but it doesn't depend on the concentration. This second term comes entirely, if we trace everything back, you notice I made this dark green color, and this is the dark green color, and these terms are also the dark green color. And there's the dark green color again, and if we go back up, there's the dark green color. These terms that are dark green, if you trace them through all the algebra here, the dark green terms are always the same as we go through the algebra, and there it is at the end. This term came entirely from the term that accounts for the translational degrees of freedom, the translational microstates of the system. And it's the only term that depends on concentration. And so I say those things down here. This term comes entirely from the translational microstates, the ability of the molecules to move around in space. They account, if you like, another way to put the same thing is they account for the entropy change, the entropy due to the freedom to move around, right? There's some entropy associated with this. There's microstates associated with this, therefore there's entropy associated with this. This term doesn't depend on what type of molecule. It's universal for all molecules. Even when I start changing the nature of the molecules, this term changes, the front term changes, but the second term, the back term, always stays the same. All right. And with that, I think we'll stop and we'll pick up the next topic in the next lecture.